Hi, today we're going to be talking about conductors and electric fields. So first, I just wanted to go over how to create a uniform electric field. You'll do this by placing two metal plates with opposite charges across from each other. So that'll look something like this. So you'll have one plate with positive charges, and then another plate in the same size and length with negative charges. Now what this will do is it'll create a uniform electric field between these plates in both strength and direction. On the edges, it won't be quite as uniform, but that won't have too much of an effect. And if you wanted to eliminate this, you would just put the plates closer together. Now, if you were to put a charge in between these plates, it would accelerate through with uniform acceleration because there's a uniform electric field. And this is the concept behind an electron gun. They put an electron between a uniform electric field and it'll accelerate and shoot it out. And this was widely used with computer and television monitors early on before they switched to flat screen TVs. So now that we know the effect of an electric field now that we know how to create an electric field, we're going to learn the effect of an electric field on a conductor. So it's important to remember that a conductor contains free charges that move around easily. And so when these charges are placed in a static electric field, they're going to want to move to reach a state called electrostatic equilibrium. An electrostatic equilibrium is the condition established by charged conductors in which the excess charge has optimally distanced itself so as to reduce the total amount of repulsive forces. So what this looks like, so say this is our conductor and we have some free charges floating around, and these could be both positive or negative. The electric field is going to have both a parallel and a perpendicular component. Now, this parallel component of the electric field is going to create a force parallel on this charge, and it's going to cause it to move. So, as it moves, it'll move to the surface of this conductor until there's only a perpendicular component to the electric field. If there's any parallel component still existing, the charge will still be moving. And so we need it, for it to reach electrostatic equilibrium, it needs to only have the perpendicular force. Now, if you were to place, when this happens, if you were to place excess charge on a conductor, they're all going to spread out like this because they all only want perpendicular components. So it'll create an electric field just like this with all perpendicular components to each charge coming off. And outside the conductor, the field is going to look exactly the same as if the conductor were a point charge. And then inside, it's important to remember that inside the sphere, there is zero electric field. Now, when you place a conductor in an electric field, it's going to polarize that conductor. So that'll look something like this. You'll have all the negative charges on one side, and all the positive charges will be pushed to another side. And the charges are going to move until the electric field lines are perpendicular to the surface. So that'll look something like this. You have the field lines coming in on one charge and coming out on the other, and these are all going to be perpendicular. And what you'll see is no electric field lines are going to exist within the conductor, and that's because within the conductor, the electric field is always going to be zero. However, the electric field is going to be increased around the outside of the conductor. Now, so just a quick review of the important concepts we've gone over so far. The electric field inside a conductor is always zero. Outside the conductor, the electric field lines are perpendicular to its surface, ending or beginning on the charges on the surface, as seen above. Any excess charge is always going to reside on the surface of a conductor, and that's what we saw here. We got excess charges, so it's going to move to the surface and create perpendicular electric field. Now that we've looked at what electric field lines look like on a spherical surface, I want to go over what they'll look like on an uneven surface. So say you have a pear shape where it's fatter here and skinnier here. Excess charges on a non-uniform conductor are going to become concentrated at the sharpest points. So when you add excess charge, you'll see that the charges all want to come to this pointier area, but they'll spread out along these fatter areas. And this is because electrostatic repulsion of like charges is most effective in moving them apart on the flattest surface so that they become less concentrated. And this is because the component parallel to the surface is greatest on the flattest surface, so it's more effective in moving the charges. So here the force parallel is greater, so they'll be more spread out, and here the force parallel up here, the force parallel is smaller, so the charges will be closer together. And this is similar when a pear-shaped or pointy object is placed in an electric field. The electric field, once again, it'll be polarized. And along the flatter surfaces, the electric field will be smaller and more spread out. But because there's more perpendicular components on the more pointed areas, the electric field will be more concentrated in these pointed areas. And this is going to be the idea behind lightning rods. So to understand how a lightning rod works, you have to remember that the Earth actually has a fairly uniform electric field of about 150 newtons per coulomb directed downward. And this is caused by a layer of charged particles surrounding the Earth called the ionosphere. Now, in good weather, the ionosphere is positive and the Earth is mostly negative, maintaining this kind of uniform electric field. However, in storm conditions, clouds form, and you're going to get a buildup of charges. And if this buildup of charges is too great and becomes larger and reverse in direction, this is when we get lightning. Now, if you can picture a tall building in this situation, the storm will actually induce a bunch of charged particles on this building, which is why when you have the opposite charges, the cloud is more likely to strike the building. So this is why people invented lightning rods. So if we remember that there's going to be an increase of charges at the more pointed surface, then with a lightning rod, which is going to be very pointed, there's going to be this huge buildup of charges right here. So you'll have all these charges coming off. And because the buildup of charges is so great, some of these charges are actually just going to come off of the rod, and so it's just kind of bleeding out these excess charges so that it's less likely for this buildup of charges to occur and for the lightning to strike the building. Now, the opposite of this is the idea behind a Faraday cage. So in a Faraday cages, all these charges are going to kind of spread out evenly across the surface. So you'll have charges just spreading out. And they're actually going to cancel out inside of it. So although on the outside you have an electric field, if you remember, all the charges and field lines will be on the surface. So inside the cage will have zero charge and zero electric field. And this is why during a storm, it's actually safer to stay inside your car because your car is going to act as this Faraday cage. And so all the charges are going to be along the outside and you on the inside will be safe where there's no electric field. that's all I have for today. I hope you learned, and have a great day.